and this is the first how-to video I've done since about 2 years ago. This one I want to talk about LaserBoy Liquid Math, which is a plain ASCII text scripting language that LaserBoy can open and use to render three-dimensional animated vector art. So as an example of that, I'll go ahead and load one. So we go input 4 for text, and LaserBoy comes with a bunch of examples. We'll load the spiral toroid, and there it is. Okay, and the first thing you see is this thing right here. That's the unit circle. This is the origin of space, the point 0, 0, 0 in XYZ coordinate system. And this is 1 unit in that space. This is the unit circle. Okay. And what we generated, the spiral toroid, is this, which in fact is a three-dimensional object. A three-dimensional line figure. Has 100,000 vertices. So how did we get here? I'll show you what this looks like. This is the script. This right here is the script for the spiral toroid. Okay? There's your 100,000 points, iterations through this that generates right here. This render is what actually puts it, it's the last instruction that puts it into the LaserBoy three-dimensional space so you can see it on the screen. Okay, so let's break this down a little bit. The LaserBoy Liquid Math script is based upon a set of predefined parameters. So these are all parameters, and these statements set their values. All right, all of these parameters are listed in the documentation for Liquid Math as parameters.txt, and you can see there's quite a few of them. All right. Okay. So, a couple of the real important ones are, in fact, start, which isn't here because its default value is 0, so we don't need to set it. But if we did, it would look like that. Okay. Duration, here we're setting to 4,000 because its default value is in fact 1. And what this means is from start to duration is the segment of the real number line that you want to use to put into whatever this generator, however it uses it. We're defining the interval from some point on the real number line for a certain distance along from that point along the real number line. And this, in this case, because it is the interval that we're using in these math figures, this is actually in units of 2 pi. And the reason being is because the unit circle, of course, has a radius of 1 and a circumference of 2 pi. So one whole trip around the unit circle is 0 to 2 pi. So this is actually in cycles of 0 to 2 pi. All right. So let's go ahead and look at this for a second. Let's rem this out because now its default value is 1. Let's rem this out because now its default value is 100. You'll see that in parameters. All right. And then we have this thing LBO1, and we're setting phase to 90, which is in degrees, by the way. And also you can change this to be in radians, or you can change it to be whatever you fractions of one whole rotation, whatever you like. But anyway, by default, its phase of an LBO is in degrees, so we're representing this here. Okay, what is an LBO? Well, an LBO is a LaserBoy oscillator. LaserBoy oscillator is a C++ class, and when you instantiate one, you get a C++ object of it. And essentially, what it is a function generator. It's kind of like, you can think of it as a modular synthesizer function generator or oscillator. You can set the waveform. By default, it is the sine wave, but you have these choices right here. You can set it to any one of those. That's the function. And then it has these expression coefficients: amplitude, frequency, phase, duty cycle, damping factor, and offset. And these are the default values. Amplitude is 1, frequency is 1, phase is 0, duty cycle is 50%, damping factor is 0, offset is 0. And these coefficients, along with this function, are used in this expression right here. Okay? So the value of a LaserBoy oscillator at t, which is time, it's actually a point somewhere along the interval, beginning at start and going towards duration. And also, t is going to be divided into equal portions of iterations. All right? By default, like I said, iterations is 100, which means that, getting back to here, so this is going to count from 0 to 99. Well, actually 0 to 100, because it puts in the last one. Anyway, so that's what this is. This is counting from 0 to 2 pi in equal increments, in 100 equal increments. So that's what t is in this expression. So then from these parameters up here that are associated with every LaserBoy oscillator class, we're using amplitude, the function, which is sine, triangle, whatever. There's t times frequency plus the phase times, this is the damping factor, this is this is an exponent, this is natural logarithmic scale, the damping factor goes there, and offset, which basically takes the waveform with respect to the 0 line, and it moves the whole thing up or down simply by adding a negative or positive number to it. And then if you put in the default values of all of these things, this is what you get if you just simply use an LBO object without changing any of these parameters. Then by default, this is the function that you get: 1 times the sine of t times 1 plus nothing times e to the no damping factor over t, which, by the way, this ends up becoming 1 times 1 plus nothing, which simplifies to the sine of t. So this is the sine function by default. All right? Getting back to the spiral toroid. Okay, if an LBO is the sine function and we add 90 degrees to its phase, it becomes the cosine. All right? So we've got LBO1, which is cosine, and we've got LBO2, which is the sine function by default. So we're going to call a generator called Lissajous. And the Lissajous generator is basically, it uses 2 LaserBoy oscillators, numbered 1 and 2. And it's simply all of the x coordinates are going to be derived from the value of the LaserBoy 1 oscillator of t, which is the number on the interval from 0 to 2 pi. And this is the sine of t. And when you plot those, well, I'll show you. Okay, we've taken out, we don't need start because we already know what that is. It is by default 0. Set the phase to 90 degrees. And we're going to render the Lissajous. Here, let's go. Alright, we'll just... let's just... Alright, so this chunk right here, between comment block start and comment block end, is now going to be ignored. Because it's a comment now. It's no longer code. Alright, so we've set, well, we didn't set. By default, start is 0. Duration is 1. Iterations is 100. We set the phase of LBO to 90, and we're calling the Lissajous generator and then we're rendering it. So let's see what this does. Go ahead and spiral. Right. Now this, as we said, is the unit circle, and the reason that it's there is because of this. We said include the unit reference. If this was not true, we simply wouldn't get that frame. So, but we said it's true, so we get this frame. So now we know the size of space that we're looking at, right? This is the origin, the point 0, 0, 0. This is the point 1 on X, 0 on Y, 0 in Z. And in fact, this thing is a three-dimensional entity, marker, whatever you want to call it. It shows three-dimensional space. Here we are looking on straight into space, and we just rendered this, a circle. All right? Okay, so where does the circle come from? Well, we already said it comes from cosine on the x-axis, sine on the y-axis, and we can demonstrate that this way. All right, we're looking straight into space, so let's change something here. All right, we go into the visual interface settings, and we're going to turn J on. See, currently our display is X, Y, and Z. Well, I'll show you. Let's put in the floating axes, F. So now you can see the floating axes, and see there's Z, X, Y, and Z. Okay, back to here. Now, let's change that. So now J, hit J. Now, the Z is gone and has been replaced by T, which is like time. In other words, this is going to show you in the depth of this cube. It's only going to be showing you X and Y coordinates, but the depth of it is now the order in which those vertices are being drawn into the frame, which corresponds to time. So out of here. Now you can see this is a three-dimensional thing, but it's no longer, right? If we look at it like this, where we're looking straight into the side of it, that is a sine wave, right? Looking straight into it again, if we look at it like this, rolling it forward, like that, these are all the x coordinates. Nothing but what you're seeing here is time is going up and down, and this is x, all the x coordinates going around the circle. And of course, you probably recognize that if you look at it this way. That's cosine. So, as you can see, the circle is where sine and cosine comes from, and if you use sine and cosine, you can generate a circle. So back to our code view again here. All right. So we've determined that this thing draws a circle, right? So if we put this back in to it, basically what we're going to get is 4,000 iterations of a circle. In other words, it's going to be the circle just drawn over itself 4,000 times. And to demonstrate that, but make it a little bit easier to see, let's just make it 40 times, and I'll show you what I'm talking about. Okay, see, there's 40 times around a circle, you see. And the reason it's stretched out like that is simply because that's how we're looking at it at the moment. It is, in fact, if we go back in here, and you turn J off, now we're putting Z back into it, and we're getting a genuine three-dimensional XYZ display. See, it's just a circle. It's just looping around on itself 40 times. All right, back to the code. All right, so let's make this again. We'll go ahead and make this 4,000, right? iterations is 100,000, okay? And this is the circle. So now let's look at this next thing that we're doing in the script. All right, and that would be this part. All right, we're defining this thing. Well, we're not defining. We're setting the value of the fulcrum, which already exists. It's a parameter that's already defined, and its default values are the origin 0, 0, 0. We're setting it here so that it's 6 units above the origin on the y-axis. So it's still at 0x, 0z, but it's 6 units above the origin on the y-axis. And we're setting rotation here, which is also a three-dimensional thing because you can rotate around the x-axis, the y-axis, or the z-axis of the fulcrum, right? We're setting x rotation to 40. And what that means is, okay, you know, you got x, y, and z. X is the horizontal. So if you're rotating around x, it's actually rotating it's bringing the whole thing into three-dimensional space because it's rotating through the y-z plane, okay? 40 times. So this is like a big coil of wire, okay? All right? Going 40,000 loops of wire, right? We set the fulcrum to 6 units above the origin because this thing is sitting right on the origin with its center at the origin. And rotation acceleration we're saying here is 0. We'll get to what that is later. But we're rotating around the x-axis 40 times, and we're calling an operator called spread rotate. Spread anything means to distribute the effect throughout the entire set of vertices. From no effect at all from the first vertex to the full effect on the last vertex, and all vertices in between getting some portion along the way. All right? So a spread rotate does just exactly that. What it's going to do is going to take this coil of 4,000 circles and it's going to like stretch it out like a slinky, but it's going to loop it around 40 times. So let's see what that looks like. All right? See, we still have our render right here. So we're doing setting the fulcrum, setting the rotation around the x-axis. This is the default value of rotation acceleration, but it's here just to show that there is such a thing. And we're calling the spread rotate operator render. Okay. There's the unit circle, okay? And you'll notice it's not at the origin anymore because, if you recall, we said that our fulcrum was 6 units above the origin. And by default, LaserBoy will figure out whatever it is you want to render, figure out the size of that thing, and put it, and it'll center it into this display space when you call render. You can, in fact, override that behavior and you can say, no, I want the origin to be at the origin. But by default, it just says wherever it is in three-dimensional space, find it, scale it, size it, center it into here. So that's why this is down here. So for the sake of seeing this a little bit better, let's take the vertices out. Okay, so there's the unit circle, and here's what we rendered. And if you turn this, you can see it is like I described. It is three-dimensional and it's going this way, okay? And this point right here that is in fact the center of this display is the point 0x 6y 0z. That's the fulcrum that we rotated around. And you can't see it because it's laying over itself, but there are 40 full rotations of this coily thing, and each rotation lays right over the previous one, so you can't see that there's 40 of them there, but there are. And this thing, it appears as though it has no beginning or end, but it certainly does. It has a beginning and it has an end, and they just happen to line up perfectly. Okay? So that's what we got so far. So now what's the next thing that we're doing here in the code, and that is we're going to do we're going to set the fulcrum again, this time to 30 on the y-axis, which is quite a bit higher than this one even, but now we're 30 units away from the origin of space, okay? And it's 0x and 0z, so this is on the y-axis, 30 units above the origin. And we're setting the rotation to only one full rotation, but not around x, but rather around z. Now z, of course, is the one that you look straight into, right? This is z, and x and y, x goes this way and y goes this way, so this is z. So rotation around z is like this, okay? One full rotation around z. Again, there's no acceleration on this, and we're doing the spread rotate again. It's the same operation we did here, but we're doing it here. But like I said, around this time we're doing it around z. So that thing that's going this way 40 times around, we're going to take it and go like this and put it back onto itself. All right, see what that looks like. Now here's the unit circle, and you'll notice it's rather small because remember we set the fulcrum to be 30 units above the unit circle, right? So there's the origin of space, 0, 0, 0. This is the unit circle, that's 1 unit. And this is what we just generated. Because remember, it was the coil 40 times around this way, and we just went like that. And as you can see, it is in fact three-dimensional. Okay? All right, and then the last thing that we do in the code, the script, is we'll just take this out and we'll take that out, and we set the Hughes span factor to 39 and Hughes shift to 5. And Hughes shift in this case doesn't really have any effect because we're only looking at one single frame. Hughes shift has to do with animating the way the Hughes palette moves through a set of vertices. But the Hughes span factor is relevant here because what we're saying, Hughes is actually a palette of 1530 RGB values that are all fully saturated hue. This is, in other words, it is the most vivid color you're going to get out of an RGB display, or whether it's a laser projector or a video monitor or whatever, it doesn't matter. Hughes is Hughes. Okay, so anywhere you're using RGB values. So there are 1530 different combinations of RGB values that represent pure vivid hue. And what we're saying is we want to cycle through that palette of 1530. We want to do that 39 times throughout the entire set of 100,000 vertices. So this is 39 as opposed to 40, because remember there's 40, if you remember, there's 40 loops in this thing, and then we go around this way. So there's like 40 kinks in it going around, right? So if we set this to 39, it creeps backwards a little bit around the whole thing in the way it colors it, and you end up with this, okay? And as you can see here, this is the palette of hues going around the inside of it there. Well, it goes around the whole thing, but you can see it makes like one cycle of the whole palette through all of these because of that slipping backwards business. Okay. All right. And if you want to see what I'm talking about there, if we make this 40, which equals the number of loops, do that. See? Now they're all the same color. Because each time this loop is going around, it's doing a total full cycle of the palette of 1530 colors. All right.